Hey everyone, and welcome back to Rocks for Jocks. My name is Alex, and I'll be your host for the show. Today I am again hosting Marshall Pontrelli, who is one of my coworkers in graduate school and one of my first guests on the show a very long time ago. Marshall joined when I was first getting started with this podcast in early 2024, so both the show's audience and my own interviewing and production skills have grown since then. So I'm taking the chance to interview him more thoroughly, get a better sense of his research, and a better understanding about how that work relates to his geotechnical engineering job in the real world. Before we get started, some very exciting news is that I've recently started a Substack, which is a website for me to share long-form science writing. When I publish any writing or podcasts, subscribers should get email newsletters sent straight to their inboxes. So depending on what's going on in my life, you might get hopefully around one podcast episode and one written newsletter straight to your inbox every month. In my opinion, this is the easiest and best way to get science content. So I'll be putting a link up in the episode description for this. So yeah, just go click on that, enter your email to subscribe, or anytime you want, you can just Google Rocks for Jocks Substack, and it should hopefully be the very first link that pops up. Last announcement, if you like the show, send it to a friend. Everyone loves learning about science, and this show is the best one out there. So sending along to somebody will make their day. Send it to the family group chat, or a friend from college, or a friend from high school, or maybe a long lost cousin you've been trying to reconnect with. I bet they will love hearing all about Earth science. All right, now let's get on to the show.
It's great to be back on the podcast. This is just one of the more electric media pieces I've ever been a part of, so it's good to be back. Yeah, in grad school, I was in the Geosystems engineering group at Tufts University, specifically in the Geohazards group. So we had a lot of different, I would say, research avenues, but in my mind, at least, there were two core avenues, and that was site response, which was that was what I did. It was a very specific thing that our advisor, Lori Bays, did in her graduate school studies, which was physics-based. It was about how waves propagate through the near surface during earthquakes, and how the properties of the overburden material and the soils changed the wave propagation of the earthquake, and how that manifested itself in human infrastructure, how it shook buildings. So that was I would say that was where that group arose from. If you read Lori's dissertation, that was all three chapters were about transfer functions and things like that, which are in the site response world. Where she took the group, and it was kind of like a natural progression, I think, was into more general hazard mapping, which is in the world of risk. So trying to map out risk in different areas with different metrics, physics-based metrics, more statistics-based methods. So I would always imagine, again, the site response world is just a single point on a map. Traditionally, you're designing a building and you figure out the soil profile and you figure out that it has a high site response hazard or it doesn't have a high site response hazard, and there's certain parameters and metrics that help you make that decision, help you figure out how the ground's going to react. And then you can move over 500 feet, and there's similar properties, but they're slightly different. And then you can move over 1,000 feet and 1,000 miles, and things are going to change. And there's all sorts of different hazards out there. Site response is one very specific one very particular one. But that's what a weather map is. That's what a hurricane map is. That's mapping. You see those presented as maps. So it starts from a point, and then it's about aggregating many points and getting an understand of how certain hazards change in space. I guess in grad school, I did the single point thing, just figuring out how soil profiles vibrated in different ways when they were forced by different earthquake waveforms. And then by the end of my dissertation, I was compiling data in New England. There were many points, and we were trying to get an understanding of how those changed in space based on the different major geologic structures that you find in the Northeast, which hilariously has helped me a ton in my professional life, because I now just design buildings and do geotechnical engineering reports and different designs, and it's very, very helpful to have a spatial understanding of how the subsurface works. Because you can be the best mathematician in the world, you can be the best physicist in the world, but when it comes to the world of geology, it's just, it is what it is. Whatever's down there is whatever's down there. You just have to know what it looks like, know where to find the data to figure out what you're going to encounter. So yeah, I use a lot of maps for that. That's kind of a rundown of my work in grad school and how I saw the group. But what I liked about working in a research group is everyone had their different like historical understanding of what the group did. Um, so yeah, my perspective from working on the site response problem to doing mapping was like a very unique thing that I worked on, like a way that I went through graduate school. But like you and Christina, like your first project was different than my first project, and therefore your progression was different. So I always really liked that and liked talking about it. Yeah.
Yeah. No, that's fantastic. That was a much better summary of the group I think than I've ever given on here. So that's appreciated. Yeah, and then for the listeners, so Marshall and I worked together in the same research group during graduate school for a couple of years. And then that's the same group that also had prior guests, Jeremy, Christina, and Ellie and Maggie. I interviewed more recently as well.
Cool.
Sweet. Yeah, and then to tie that to the prior episode, Maggie and Ellie, one of the things that each of them are doing is making, I guess you could say, hazard maps using HVSR readings, which is kind of a way of, I guess, tracking how the soil is going to respond to earthquake shaking waves and affect the structures over it. Did I get that summary right? Or do you have anything to change on that?
Yes, and that is what Laurie and me would argue we started doing first, is like F naught HVSR is like it's like sort of a newer parameter. It's not rocket science. Like it's just like a different measurement that you can get pretty inexpensively that gives you an understanding of site response. And like there are many of those other parameters that people have turned into maps of those parameters to help. And Laurie and I were just along at the right time where HVSR was possible, popular, valuable, pretty inexpensive to measure. A lot of people knew what it was, but no one had quite mapped it yet. And so that was what we started doing. So like my first chapter of my dissertation is just like a really, really coarse map of F naught in New England. And I highly assume that her new students' maps are way better than any of mine.
Yeah,
that was what we did. We just
stuff,
like we pulled it all together because no one had taken the time to pull all the F naught measurements together and try to map it in space.
Sweet. Okay, cool. So then maybe that's a good segue then. Can you give them kind of a quick outline of each of your three projects and kind of how they tied together? I think you did three chapters.
Yeah, I did three chapters. Two were kind of the same. So I'll throw my master's thesis in there too, which is a textbook site response problem, which is Mexico City. My like second week of grad school. I probably told this story in the first podcast, but my second week in grad school, September 19th, 2017. I hope that's right. Check me in the comments.
Yep.
September 19th, 2017 was an earthquake near Mexico City that caused a lot of damage, and it was coincidentally the on the same day as the 1985 Mexico City earthquake, which caused huge amounts of damage. This one in 2017 caused huge amounts of damage too. And Mexico City's built on this like really soft clay profile that resonates like crazy, and that resonance is what knocks buildings down. And so it's kind of it was a great excuse. There was this big earthquake. There's a ton of data there because of the 1985 earthquake. They instrumented the heck out of the city. So we got in touch with it's called UNAM. It was in Spanish, but National University of Mexico City. And got access to all their data and processed it all and sort of mapped out the fundamental resonances and the basin structure of Mexico City. So that was a great exercise. We were using a really rich database of events. Learned a ton doing it. And then we had some funding that turned into like my whole dissertation, which was basically like applying all of these techniques to New England, which there's not a lot of earthquakes. and like the USGS wants to map it, but there's not a huge amount of funding. So we got some of the funding, and we knew how to do all of this because Lori's worked in Japan. That was a I think that was probably the first big Mexico City project she did when it was my master's thesis. I could be wrong about that. I know a lot of her previous students worked in Japan because they have a great database too. But yeah, we had this like great like basin study in Mexico City. I knew how to do a lot of the techniques, and then we like brought it all back to New England, where you and I both worked at Weston Observatory at BC, that has a bunch of geophysical equipment. So I got to collect some of this data that you can use to understand these ground properties, and we basically did really similar things, but with like way sparser data, which was a challenge. So we ended up using a lot of geologic data. There are good geologic maps around here, and the geologic maps are really good for estimating. Not really good, but they're well correlated to mechanical properties like shear wave velocity, which is the crux of site response. And then shear wave velocity is one of the main pieces of site response, and geometry. And there's a wealth of water well driller database, borehole data in Massachusetts, and really in all the states. Some are harder to get. The Massachusetts one you can just download. I use it every day at work. Super valuable database. We took that. We took that. So we sort of knew depths. We knew basic geometries. We obviously knew topography. And then we went around and collected a lot of our own data to fill in the gaps. So yeah, it was cool. It was kind of like a textbook area to study site response in Mexico City. Yeah. And then it was like here.
Can I jump in with a quick question?
Oh, yeah, sure.
On that? Yeah, so just a quick question on kind of how all the puzzle pieces fit together. So the geological maps we have from lots of prior researchers can kind of go underground and see what's there, basically. Yep. Then the other part of that you want to have for earthquake engineering is the layers of soil that's kind of sitting on top of the rock. So the geological maps, quote unquote, are, if I remember right, are mostly just about the bedrock, like the hard stuff that does not move.
We have the soft,
and then we
have the soft stuff too. Superficial geologic maps.
Right.
Yeah.
Yep, exactly. So you want the superficial geologic maps. And then the other part, I guess, that our group has worked on in the past is taking instruments that are put out before earthquakes occur. And then when the earthquake waves move through the area, you can see which points respond to the earthquake waves in different ways. Yep. And then you use that to kind of get more information about how the soils, those specific soils, respond to earthquake shaking waves. Yeah. Which then can be used to make a hazard map and see how the soil maps are going to respond in the future to like a general earthquake shaking in the area kind of thing. Is that right?
That's exactly right. Yeah. Yeah. Use the information that you've seen in the past, any information you can get to make a prediction about how how the soil will respond to future wave or earthquake triggers. So yeah, there's like characteristic earthquakes that you would load any of these near surface profiles with and come up with an estimate of what the output shaking is going to look like at the surface, and then you can turn that into like a response spectra, which is that's what a structural engineer would design a building to. So those are the different loadings that a building is expected to see at different actually they do it in periods, and then they basically have to design the building to meet more capacity depending on how strong the expected forces are going to be. So that's the combination of the magnitude of the event. So like in Massachusetts, those are like small estimated magnitudes, and the site term, which is what we worked on. So how much a typical magnitude earthquake is going to be amplified by the near surface.
Right. And then just to clarify, the response spectra is basically like a basic graph from geometry class of XY axis, and you see more of a response at different frequencies, which then lets you know what frequency to build the building. Am I thinking about this the right way?
Yeah. I mean, how you calculate a response spectra is you take any forcing function, which is like frequency versus amplitude. So it would be like an earthquake. You could run an earthquake through a response spectra, and you're imagining a building of a like single mass damper building at a single frequency of, and you loop through every single frequency. So it's how every building at every frequency is going to respond to this particular waveform. And so at some frequencies, that mass is going to amplify at greater amounts. It's the same as if I'm pushing every 6 seconds. If
Mhm.
my swing likes to swing back and forth at 6 second intervals, then it's going to go really, really high. But if I'm pushing at 4 seconds, then I push my kid, he comes back and he's only right here, and I push again and I miss him and he starts to slow down. But if he's swinging and I'm
Mm.
pushing at the same frequency, he's gonna go higher and higher and higher. But if I'm at a weird frequency, he's gonna slow down and slow down and slow down. And so that's
That was a
yeah.
great metaphor. I've not heard that metaphor before, but I like that a lot.
Another funny one that our earthquake engineering professor Juan Pastana did to teach fundamental resonance was there's a frequency at which getting yelled at to clean your bedroom will make you clean your bedroom. If it's once every 2 days, you're probably not gonna ignore it. But if it's like once every 4 hours, you'd be like, oh my god, okay, I'll, I'll clean my bedroom.
And then if you get yelled at too often, you're probably gonna ignore that too.
Yeah, exactly. You're just be like, this is, yeah, it's not, it doesn't have any effect. Like you're just, yeah, you just put on a recorder that's doing this over and over again. I'm just gonna ignore it.
That's funny. Okay, great. And then one other thing you mentioned there, I want to get a better sense of is you said you were also looking at uh, mapping out major geological structures to help you kind of get a better understanding of how earthquake waves affect what actually happens on the surface of the ground. Yeah, could you just talk about that again for a
Yeah,
minute?
that was my favorite thing. That still is my favorite thing. I separate hazard mapping from engineering. Like engineering is like you're drilling borings, you're collecting site specific data, and you're making predictions based on like a very particular location using like a very like granular set of techniques and granular data. Um, that was like the site response thing of Lori's group where we were doing like particular profiles of soil and running, figuring out how they were going to affect earthquake waves. Um, Geologic mapping and hazard mapping is, I think, like a really, really fun to do as like a human brain because it's like more broad. You're giving yourself like
Mm.
broad, generalized understandings. Your metrics are like instead of it is going to amplify exactly 4.7 times at a frequency of or at a period of 1 second. It's more like the city of Boston is a generalized profile of about 10 to 20 feet of 10 to 20 feet of anthropogenic fill over glacial outwash deposits over 10 to 20 feet of glacial outwash deposits over 100 to 120 feet of marine clay deposits that were deposited in this way following the Wisconsin glaciation period over glacial till over Cambridge argillite. And so and it's going to vary in depth and vary, but like you have this broad understanding of what you're going to encounter, and that is a really, really valuable like starting point to do like deeper, more granular engineering. Um so yeah, that was what our work was like. um
You like drilled into the ground, pulled up a bunch of soil and rock, and figured out what was at different depths. And then did you map that out in kind of 3D space
so
across a bunch of different
we
locations, or how'd
we
that
didn't do
work?
any drilling, and I would say we didn't do any like granular studies. We took a lot of data from people who had compiled a lot of drilling and made geologic maps and depth to bedrock maps. And then we measured the parameter that we wanted to map, which was F naught. Yeah, so we were measuring F naught at the surface because that was something that we can measure. And then we were saying, hey, it's changing in this way. Like I went out to Springfield and I took like 30 HVSR measurements, and the frequencies are low adjacent. I don't actually remember what it was, to be honest, but I think the frequencies are low adjacent to the Connecticut River, and then they get higher and higher as you get up into the hillier, surrounding tills. And you look at a geology map and you look at nearby borings. It's like, oh yeah, like bedrock gets deeper and deeper and deeper, and the geology shifts from tills, which are like compact um, glacial deposits with high shear wave velocity, not a lot of site response, and it turns into floodplain alluvium, which is like unconsolidated loose sediments deposited by the Connecticut River. Oh, and lacustrine clay. Yeah, there's glacial lake clay underneath the alluvial deposit, so it's high site response. And that was manifested in our study as a decrease in fundamental resonance. Um, if you were designing a building, you would drill and you would look at the exact profile and you would say there's 40 feet of lacustrine sediments underlying 20 feet of alluvial deposits from the Connecticut River, underlying 5 feet of fill, underlying 1 feet of topsoil. I'm going to run a 1D site response analysis on this, and I'm going to see what the transfer function is through the overburden, and I'm going to use that to inform how I design my building. So like what we did was more broad, and then you would use that information to do more specific things. And that's frankly what we do. I work at a geotechnical engineering firm. We start every single project. We have a big GIS database, and we go look at all the geology maps, look at all the nearby borings, read the old reports. We have to write like a 2 or 3 paragraph thing for our proposals before we're getting paid or anything like that. That's just like, here's what I think it's going to look like, and here's how I think that's going to manifest itself.
And I'm going to ask you for one more metaphor here that I know I've heard from you in the past. Do you also have a metaphor about playing guitar strings in terms of the frequency
Yeah,
measurements?
yeah. Guitars. The tension on a guitar is like the stiffness, which is the shear wave velocity, and the length of the guitar is the depth. If you make the length of the guitar string longer and you keep the tension the same, the frequency is going to drop because the tension is the same. The time that it takes the wave to go to one side of the fretboard to the other is longer because the distance is longer. And if you keep the guitar the same and you increase the tension, you're increasing the stiffness, and the waves are traveling faster, so they're going back and forth faster. In geology, the stiffness is how the shear wave velocity is the stiffness, so how hard the soil is. So like soft organics and clays have low shear wave velocity, and like compact tills and anything compact and dense has a higher shear wave velocity. So in those, waves are going back and forth really really fast because they can travel. It is a higher shear wave velocity, and in the lower velocity sediments, the waves go back and forth slowly, and so the frequency is lower. And then the geometry part of it, the length of the fretboard part of it, is the depth to bedrock. So the deeper the depth is to bedrock, the longer it takes the waves to go all the way down, hit the bedrock, and come all the way back up. So the frequency is lower. So deep soft sediments have low fundamental frequencies, and therefore tall skyscrapers with low fundamental frequencies or long periods, which is how structural engineers work in, um, they will resonate. They will be more significantly affected by lower frequencies. But that's what's interesting about studying it is it kind of depends. Like you can build a skyscraper on really low shear wave velocity, high site response issue sediment if there's a shallow depth to bedrock because the frequencies are going to be high enough that you'll be designing the frequency, the fundamental resonance of your building is going to be low enough that you will have designed away from that frequency. So those are the two major things, and then there's like an infinite amount of like more specific nitty gritty stuff that goes into modeling. I hated that. Like I hated trying to perfectly match like single waveforms and figure out every single thing, and because then it just completely breaks down when you move on
Really?
to another site, and you're like, what are we doing? So I like in the world of geology, I definitely like the broad thinking to the fine grained nitty gritty thinking, and then
Yeah.
just put a little factor of safety in there, and you're good enough and efficient enough.
Okay, great. And then I wanted to follow up on one thing about the shear wave velocity. So that's something you mentioned a couple times here. For the listeners, earthquake shaking has a couple of different types of waves that it releases. The shear wave is typically the strongest. So it's the one that engineers will pay attention to, I think, probably the most often when they're trying to make buildings or bridges or other types of infrastructure resistant to shaking.
I wouldn't say it's the
Um,
strongest. It's just that shear is usually the mode of failure that things have. So like shear
yes.
waves like come up to the surface horizontally, and so they shake a building like this. Whereas like compressional waves are gonna, it's harder to break something in compression than it is in shear.
Right. So the shear waves move side to side, and the idea is that if the shear waves are moving at the same frequency that the building naturally vibrates, it's going to take a lot more damage.
Yeah, the vibrations will be greater if the frequency of the waves that are loading the building is the same as the fundamental resonance of the building. Just like the pushing a kid on a swing example. You're not going to be able to push a kid on a swing if you're just patting them on the back. And you're not going to be able to push a kid if you do one push and then you leave for 24 hours and you do another push. But if you push them every 6 seconds, they're going to go higher and higher.
Yeah, and then to wrap up that metaphor, the kid swinging in this context is a
Yeah.
building. In buildings naturally vibrate, even if we don't feel them, even if we're inside of them every day and it doesn't feel like the building's moving, that kind of thing,
Yeah.
which is correlated to the height. I think you said as well.
Yeah.
The taller buildings move at a slower frequency. Is that
Yeah,
right?
because waves it takes a longer time for them to go all the way up and all the way back down.
Thanks a bunch. I think I kind of interrupted you a bunch of times in there.
No, no.
Did you get to the third project of your dissertation? Did you want to talk about that one as
It
well?
was so the first one. I guess I didn't break up what they were. The first one was literally just we took geologic maps and we took these points that were measurements of F naught and we literally just did the
Mhm.
statistics on what typical F naughts were in different geologic structures. So like in Boston, marine clay, the range of F naught that we find from our 87 data points is between 1.2 and 2.3. In the Connecticut River Valley, alluvial floodplain alluvium deposits from the Connecticut River, the fundamental resonance ranges from zero point 0.9 to whatever 5.5. So it was like that was it. It was just like it was just like compiling the database and then just coming up with like a broad understanding of what the typical frequencies are going to be in typical areas. And then the second chapter was we did that and just did it way better. Like I used a national map, and the second chapter was basically like I had to compile um, local maps, so higher resolution geologic maps. Turns out to be super hard. There's like a whole world of I was not qualified, or like it should have been a big team making. There is a team at the USGS who is doing this that I was talking with, and like they were having trouble like making all the lines line up and everything like that. So I sort of like grouped all of those geologic maps using other data. That was like how I made the decisions. But the map that I made is not the definitive geologic map, but it spat out a good enough higher resolution fundamental frequency map based on these geologies that it was pretty helpful. But the third chapter was the best in my opinion. I'm in the second round of edits as of like a week ago with Earthquake Spectra. Just like yeah, trying to finish that. It's been a. I mean,
Still getting the papers published from that.
yeah. I mean, yeah, it's a huge pain, but it's totally reasonable and all that. Yeah, that one uses the depth to bedrock map in Massachusetts that I got to help on during grad school,
Mm.
which was a great experience. That was like one of the cooler experiences I had in grad school. And they took all of the water well drillers database wells and took the depth to bedrock value from there and built this surface of bedrock in Massachusetts. And what that allowed me to do is because fundamental frequency is a function of depth to bedrock and shear wave velocity. We have a decent amount of shear wave velocity measurements in different geologies, so I have a pretty good estimate of what the shear wave profile should look like in different geologic profiles. And then because we had this surface, we had a depth to bedrock everywhere, and it was a pretty simple calculation. But there's just a ton of data because the depth to bedrock map was a 100 foot by 100 foot grid. And so like you click on one of these pixels and you get a depth to bedrock estimate. We provided an estimate of the shear wave velocity and from the geology and from these other shear wave profiles we have in the region. And then it spits out an estimate of F naught. So like, yeah, it was just like a great, it was just like a great way to estimate this parameter, just because we had the data. Like, it wouldn't have been a possible project to do if that F naught map hadn't, or if that depth to bedrock map hadn't been published. Um, so yeah, I got to work on that team, which was cool because they wanted me to calculate VS30, which is the current code requires. The current code has site classifications, which is how severe the site response is based on this parameter called VS30, which is the average shear wave velocity over the top 30 meters of material. And what our argument is like, yeah, that's great, but that's only half of the site response equation. The other half is the depth to bedrock, and that's why we really wanted to use F naught. But because the state of the practice is the state of the practice, the Mass State geologist wanted me to make a VS30 map based off his depth to bedrock, which was a similar
Yeah.
process, but we just calculated a different number.
And then is F naught, is that also cheaper to take measurements of out in the field?
It's really inexpensive to take in the field. I mean, now that I've been practicing for a couple of years, um, like the answer is just like always it depends. Like, I just did my first cone penetration tests on a project in the Lake Albany clays. I got to be out there, do the borings, pull out the split spoons of clay.
Can you remind me what that is, the cone penetration
So the
tests?
cone penetration test is literally you just push a cone into the ground and you get a tip resistance and a skin friction off the cone. So what that is how hard are you pushing? How much is you pushing, letting this cone go through the subsurface? So if you can imagine pushing it through like a till, you can't even do it. You can't even do the test through harder, more compact materials. But for softer stuff, you can imagine like pushing a cone through jello would be pretty easy. Pushing a cone through a pound cake would probably be a little harder. Pushing a cone through like pasta would have sort of different, it would slip a little bit more. Um, so that's what a cone penetration test is. They also equip them with seismometers, and you trigger it. You as you're pushing the cone, you stop every 5 feet or 2 meters, depending on what you want, and you generate a shear wave, and it goes down to the point at which the cone is, and the depth that you're at, so you get a shear wave
Mhm.
velocity. And so I just watching
And
this.
that's usually done with like usually done with like a hammer or something,
Yeah,
right? Like
the
dropping a
trigger.
hammer on
So
the
the whole
surface.
thing is a drill rig. The drill rig is pushing it, and then you hammer. You generate the shear wave with a hammer, and that gives you like a way better velocity than anything that Lori and I were doing. So it costs a ton more, but if you're doing a site specific project and engineering a big building, which we are for this one, it's absolutely the move. I wouldn't do an HVSR survey there. Like, we need to do a cone penetration test for other things.
Mhm.
However, in the world of like hazard mapping, which people use to make decisions, and like insurance companies use to make like broad hazard maps, like you worked on, you can't do a ton of cone penetration tests. It costs like $5,000 to do one of them, and you get 1 point. Whereas the HVSR, which is the technique used to collect data to calculate F naught, you can do that really, really quickly, and you can get a lot of numbers from it over a pretty broad area, which is what you need if instead, rather than thinking really, really granularly about this one particular structure and how it's going to react to whatever forcing there is, you have a different problem, which is like, I have a huge portfolio of properties, and I need a broad understanding of how, if there were an earthquake in my city, how, or maybe not properties, I am like a city leader, and I need to develop like an evacuation route for my population. Like, I want to know what general area of my city might see the greatest destruction following an earthquake. Okay, here's a city, here's a big neighborhood in my city that's all unreinforced concrete buildings that are 4 stories tall, over 60 feet of clay. I think that's probably the worst. That's the highest hazard, highest risk, and therefore highest hazard area of my building. So it's a different. It's like a different. It depends. Like that. I like really F not for what we did in Lori's group. I think was like the best. Like, it was just pretty easy to collect, really easy to compute. You could get a ton of it. You could glean a lot of really imperfect information, but still way better than nothing. And you could do it really quickly. So that was where it really shone. And that was how Lori and I ended up doing all that.
Okay, so then one other thing I wanted to mention, you were talking about still working on papers here, even though I've been out of grad school for a bit. That was one thing that I was not expecting when I finished up my master's. Was it took me about 2 years to get a paper published. Part of that was definitely on my own side, where I probably should have looked at the projects I was doing early on. I probably should have split that into like two different focus areas and either publish them separately or only publish one of them, kind of thing. So part of that was definitely on me for like not cutting it down early enough. And then to make it small enough, it took about a year of going back and forth with the two professors I was writing it with, one of whom was on sabbatical. So like obviously I wasn't going to press him and make him rush through it. And then another year of going back and forth with the editors of the paper. Yeah, I guess I was wondering kind of how that process has gone for you in comparison, and like how, if you've had any of them published yet, and like if so, how you felt the process went for you.
Yeah, I know. I've one of my first chapters published. It's in engineering geology. Um, my third chapter is really far along, but I'm getting like grilled. So like we're putting in a ton of effort, but yeah, again like I like send in my revisions and then they come back like 8 months later or 6 months later, which I have a lot of respect for. I know a lot of the people at the journal. It's not like I'm not like frustrated. I'm not like mad. Yeah, to be honest, like I'm an advocate of peer review. Like I am not in a position to. If I were a tenured professor, I would have more of a machine in place to have a lot of papers in review, so you're constantly kind of working on everything at the same time, which is how my company works. Like we work on a ton of things at the same time. But because I went into the industry, like I'm not incentivized to make a machine to work on my papers in an efficient way. So I'm just doing one at a time, which is not an efficient way to do it. So I think the long time horizon makes sense. Like I've had to address a lot of issues that are valuable and like right. Like yeah, no, you guys are. That was a good point. Like I kind of screwed that one up. Like yeah, I'll change that. And that takes a lot of time. But what you're supposed to do is you're supposed to be a tenured professor and have like 25 of these going at once, and then one pops out every couple of weeks. I mean, that's what my company
That's
does, but it's
brutal.
fine. Like it's just more efficient. Like it takes a long time to write a good paper. So you just do a bunch at the same time and work on them slowly with this team. So I've like learned that as I've started working that way at a company. Obviously, we're not creating peer-reviewed papers. We're creating like reports, stamp reports, stuff like
Mhm.
that. Um, but yeah, it's exactly how we work. Like things like change and projects slow down and speed up. Um, so yeah, like I don't mind doing this. Like it's the right way to do it. Like I like often find the process really valuable, but it's definitely like I'm not in the most efficient place to rank I've learned that sort of basically. I was like, yeah, if I were a tenured professor, this is how I would operate. I would just have a ton of things going at the same time, have relationships with all the journals, and work
Yeah.
work with them over time. Where my downtime waiting for one of my papers to get edited, I'm working on other stuff. Whereas right now, because I'm not doing that's not what I'm doing with my career. I'm waiting 6 months, then picking it up again from scratch.
Do you think there is a way to do this on a shorter time scale? Do you think there's any accuracy trade-offs that you would accept for if like some really interesting results came out that was relevant to something coming up in a couple of weeks or a couple of months? Do you have any thoughts on like ways that people can accurately get those papers out? I know that like during the COVID pandemic, this was a big deal with biology and biomedical engineering papers of trying to kind of do that trade off of speed versus accuracy kind of thing.
Yeah, I mean, it depends. Like, do you want it done right or do you want it done right now? Like, I, like for my first paper, like one of the people who edited it, I was just like, dude, this is not important. Like, I'm sorry, this is like the simplest paper ever. Like, anyone can go and read that method section. I wrote it very well. It's very clear, but it's not hard. It's not rocket science. Some of the data is probably wrong. I'm sure those ranges of estimates, I'm sure you could recalculate it and get different numbers, but that wasn't the point of the paper. But like for this one, I'm like, to be honest, the first round of edits that I got on this chapter, which is, I think, the most valuable thing I did, and it's the thing that I'm having the most struggle actually like make perfect because there's a lot going on in there. And one of the major contentions that they've had with it is like a pretty fair contention. And like yeah, if I were like really like there's a lot of work that I have to do to address that. Like that's an instance where I'm like, yeah, this is just gonna take time. Like I don't want it to. Like I don't want to do this anymore. I wish I had done it right the first time. Actually, that is how
Mhm.
I would change it. To be honest, is more, and this is the same in the private industry too. In certain structures, is you working in a vacuum and then presenting it to people and then bring it back. It would be great to have as you are going through the process, you know who the editorial team is going to be, and you vet decisions on the way there. That would be, I mean, it would be impossible to do, but that's the most annoying part. If someone
Mhm.
says, why didn't you do this? You're like, I don't remember. I don't like, I just made that choice. Like I made it with a team, we thought it was the right thing to do. Like you're probably
Yeah.
right, but that would have been a ton of different resources to make that decision, like a different set of
Mhm.
resources, a different path to take. Um, so I've never liked that. I've loved working on design build teams in the private industry because we have a massive incentive to do things right because we own the final product, not literally, but like we own the properties of the final product. Whereas in other
What's it designed to?
so like there's a bunch of structures in like designing, construction. Um what the most common historically, at least in public work, and I guess how a lot of private work gets done too, is design, bid, build, where there's a design team. They design the entire building, like soup to nuts. It gets put together in a package with like specification and drawings, and then that gets bid on by contractors, and then they take ownership, and it is now theirs. And now they have to build
Mm.
it, and they have to make it work. Um, but like therefore like they do, everyone tries, like it's not malicious, like you're trying, there's a really long process where they can ask questions and they can like, we make tons of edits, um and they make sure everything is okay, but it's like a huge package of thousands and thousands of pages, like stuff gets missed, and then the ownership is passed on to them. So like if you did a bad job with the design and something that you have shown is just not going to work, they never were able to have any input on that, and they're kind of screwed. And everyone loses. Like everyone loses. The client loses money, all this stuff. Whereas there are other structures like design build, where the design team and the construction team, there's another one called CM at Risk that I really like too, where the people who are going to build it are a part of the design process and they have some influence. And like, oh yeah, what you just designed is brilliant because for it's going to be really energy efficient or something like that. But it's impossible. There's not a machine that does that. Like I don't like yeah, it's not going to work. Um, and I've equated that, or right, I've never thought about this until this interview, but yeah, I equate that to like it's so helpful when like everyone's kind of on the same team the whole time. Um, and I get it, like peer review is to make sure like you don't like cheat it, like you want to get papers published and like maybe there's an incentive to cheat, like or to like cut corners or something like that or manipulate data, whatever, and that's what like peer review is trying to squash down. But like if you have generally good people, like there's got to be some other ways to make the output of equivalent quality where you have a greater decision making pool to help out along the way. And there's a lot of parties involved at making this idea work. So I don't know. I have no idea. Like that was like a very
Yeah.
general. I wish that these people had been on my team when I started, and they would have been like, "What you're doing, that's a bad
Mhm.
idea. Just do this. It's gonna be way better." But it's like I've already went down this path 3 years ago. Like I feel like the output is valuable, but I made that choice.
Yeah.
Like I don't know what to say.
Do you think you'd ever go back to academia? How are you feeling about that these
I
days?
definitely would. I would love to teach again. Yeah, and I
Really?
think that I would also be really valuable. Not because me being special or anything, but um, I've learned so freaking much working in the industry, and it's really awesome. And I realize I know which professors I had this experience, and I found it really valuable in hindsight. Like they were teaching me. I was like, yeah, you were teaching me the stuff that I do now. Like, okay, that's sweet. Like you knew what the deal was. Like I would love to go in and teach a class where the entire school writes a geotechnical engineer, or the entire class writes a geotechnical engineering report, and like
Yeah, that'd
we
be
just do
sick.
it start to finish, and that's the entire course, and
Yeah.
we do it like way bigger, but you have to do so much during that process, and we get broken out into weeks. But the way that we teach
Hmm.
right now, it's a lot of like breaking up into theory and stuff like that, but like tying it
Hmm.
all together into a finished product is what a business does. And if you could see that start to
Yeah.
finish, or not even a business, like that's my problem with writing papers. There's a long chain that you have to go through that's hard to learn. Like like it would be great where the class is just we are making this product. Every week is just a step in the process, and let's do it. I would
Sweet.
love to do that.
Okay,
Yeah.
great. There was the big earthquake a couple weeks ago under, was it one of the peninsula in Russia, right? Yeah,
Yeah.
August 6th. I'm not gonna try to pronounce that name.
Yeah.
Under a Russian peninsula. Um, yeah, and I know there were a couple foreshocks and aftershocks for that one as well. Check and see if you had any thoughts on that earthquake specifically, or just pop science in general right
So
now.
my pop science thing there, I haven't done any research, but a fun thing to learn that I think people can do um is, and I realized that I like was able to do this in a great I think it'd be a tangible way to learn about earth science is my friend or a guy I work with turns around and says, hey, did you all read about this? I mean, I work at a geotech firm, this is what people talk about. He was like, how deep do you think it was? And I was like, I think it was 15 kilometers. And I say that because I don't know anything about this earthquake, but I know it's a subduction zone up there. I bet it, and it was huge. I bet it was a deep earthquake because you need to have an earthquake that big. It's got to be really deep for there to be enough stresses to build up because there's a ton of overburden confining stress. It was deeper than what I guess. I think I said 15. It was actually 20. But you can totally learn those simple little correlations, like where are the subduction zones? How are the plates moving? Where are the strike slips, like California? And then when an earthquake happens,
Hmm.
the USGS website, you can just go click on it, see how deep it is, and you'll start seeing these patterns. And it was like, that's how we now know these patterns, and these are maps. Like I know that it's a subduction zone up here. But before we knew that,
Yeah.
we just collected all of this data. It turned into this big spread, big plot, and then it was like, oh look at the shape of where all these earthquake hypocenters are. It looks like this. Oh, I think that that's a subducting plate. And so you can kind of we now know what those patterns are and what the statistics are, but you can just you can just learn where all those where we've classified all of those things, and then you can see how the different earthquakes change in the different areas. So yeah, I don't know
Yeah.
anything else about that. I know it didn't generate a big tsunami. It generated a little bit of a tsunami, but I don't really know how any of that stuff works.
Yeah, no, absolutely. And to tack onto the USGS website thing, 6 or 7 months ago, I made a video for the big earthquake that happened up in Maine, and kind of walk through the USGS website and like how you could see the different earthquakes that are tracked in the last like 24 hours, 30 days, above and below certain thresholds, that kind of thing. Um,
I think that
yeah,
stuff's
so
great.
definitely go check out the website.
I think all those resources are so awesome. Like it's
Mm,
just checking. It's like checking baseball stats every morning. Like you just like start to learn. You start to see patterns because it's what people do, and it's a
yeah,
great way to learn and get quick feedback of things actually happening on the earth.
yeah, yeah, definitely. Okay, cool. So then last couple minutes here before we wrap up, anything else you want to talk about with regards to science in the world these days?
Um, I don't know about necessarily in the world. I definitely like the further into my life I get and the further I like operate in a society as a human, the more of an advocate I am of like scientific thinking. Because I think it's just like a position of being skeptical about things. and then learn, and then like collecting information yourself for you to try to learn, to try to make better decisions, and then update those as conditions in the world change. And I think that's applicable to absolutely everything. I don't think you have to be a scientist, but I think that that's a good perspective to take on the world. And like, at least the headline news, you're like, Jesus, what are we doing? Like, I don't think that's a great way to make choices, but you know, at the same time though, it kind of makes you appreciate humans because it's kind of more fun than like dry science. It's like way more chaotic. Like people do dumb stuff and I do dumb stuff, and yeah, so I guess I appreciate all of that, but I definitely on the average, like if you're trying to accomplish something, I do think you need to apply some degree of scientific and engineering thought to it. Um, so yeah, and I think it's fun too. I think it's just fun. Like if you're good at if you're
Yeah.
good at doing stuff that like helps propel humanity forward, you're gonna be fine. Like if you constantly have to fight for power, like that's a way more strenuous position, I think, to probably be in as a person. I'd much rather just
Mhm.
be good at doing stuff and make a
Yeah.
living that way.
Yeah. And like what you said as well about updating the views when new information comes in, that kind of thing.
Yeah. Yeah.
Sweet.
Yeah.
All right. Well, thanks so much, man, for recording this. I'm going to pause the recording here. If you've made it to the end of this episode, I'm here to let you know that you are legally required to subscribe to Rocks for Jocks Substack. Click the link in the description to this episode to enter your email and receive a free podcast and newsletter delivered to your inbox every month. Thanks for listening.